All right, master plan part 3. The story, and I think this holds together quite well, and we'll be actually publishing a detailed white paper with all of our assumptions and calculations, is that there is a clear path to a fully sustainable Earth with abundance. In fact, you could support a civilization much bigger than Earth, than much more than the 8 billion humans could actually be supported sustainably on Earth. And I'm just often shocked and surprised by how few people realize this. So we're going to walk through the calculations for how to create a sustainable energy civilization.
And to set the stage, today our energy economy, let's be honest, it's dirty and it's wasteful. Over 80% of global energy, primary energy, comes from fossil fuels, and only 1/3 of that global energy actually ends up delivering useful work or heat. This is the problem statement, but we're here to talk about the solution.
So if you have a gasoline car, you're converting less than 1/3, often maybe only 25% of the energy in the gasoline is converted into motion. The rest is turned into waste heat. That doesn't do any good at all. And there's a lot of energy required even to get the oil out of the ground, to refine the oil, and to transport the gasoline to the gas station. So when you look at all that, for a typical gasoline car is actually going to be using less than 20%, fully considered, of the energy from the oil actually goes into motion. So this is when we see people doing calculations for what does it take to create a sustainable energy Earth, they assume that the same energy amount is required for an electrified civilization versus a combustion civilization. This is not true, because most of the energy of combustion is waste heat.
But the nice thing about an electrified economy, through end-use efficiency and through efficiency along every step of the way, actually the total energy use halves. So this is one of the most enabling aspects of electrifying everything, is that the sustainable energy economy is that much easier to accomplish. It's actually half the problem statement of the fossil fuel economy.
Yeah, and we're being conservative here, so it could be better than half, but we're trying to have assumptions that are reasonable, not overly optimistic, in fact, slightly pessimistic.
So how the master plan works, you want to talk about?
The thing that is needed at very large scale that is not currently present is a vast amount of battery energy storage. Our rough calculations are that this is about 240 terawatt hours, or 240,000 gigawatt hours. So if you've got solar or wind, you've got to store the energy when the wind is not blowing, the sun is not shining. And so we're assuming sort of an 8-to-1 ratio of stored energy to power. So 30 terawatt hours of power, 30 terawatts of power. Our capital expenditure calculation for manufacturing investment is more like 6 trillion, but we made it higher to make it 10 trillion.
And this is across mining, refining, battery factories, recycling, vehicle factories, all the things that we're going to talk about needing to invest in to build the sustainable energy economy.
Yeah. Now, if you look at the total world economy, it's just under 100 trillion. So if this was spread out, say, over 10 years, it would be 1% of the global economy. Over 20 years, it would be 0.5% of the global economy. So this is, not a big number relative to the global economy. As Drew mentioned, you need about half as much energy with an electric economy versus a combustion economy. And in terms of wind and solar, how much land would be used? It's less than 0.2% of the land area of Earth. The electrified economy will require less mining than the current economy does.
Yes.
Less, not more. Okay.
So this is the plan, and now we'll get into a little bit more of the details of the plan. Basically, 5 areas of work. First, renewable power, the existing grid. Second, switch to electric vehicles. Third, switch homes, businesses, and industry heating to heat pumps. Fourth, high-temp heat delivery and storage for high-temp industrial and chemical processes, and a little bit of green hydrogen in there for chemical processes that need hydrogen. And finally, sustainably fuel planes and boats. These are the 5 areas, and we're going to go into detail on all of them.
Yeah, I mean, my personal opinion is that as we improve the energy density of batteries, you'll see all transportation go fully electric, with the exception of rockets.
So first, repowering the existing grid with renewables. And this is going to be a consistent theme. You'll see our estimates for the number of terawatt hours, terawatts, and trillions of investment at the bottom of the page. You know, this is already actively occurring in front of us. 60% of the generation added to the US grid was solar in 2022. And actually, on a year-on-year basis, solar deployment is growing 50% year-on-year as of 2022. So this is a serious upswing. And if we continue this trend, this is going to be behind us before we even know it.
Yeah.
Second, switching to electric vehicles. Again, 21% reduction in fossil fuel use by doing this alone. Obviously, Tesla is heavily engaged in this activity, along with many others. Overall, EV production grew 59% year-on-year in 2022. And what does this fleet look like? You know, just rough view from our perspective. Of course, we could be wrong, but you know, you can see the sort of breakdown of the fleet by millions of vehicles. You know, our goal is to do 20 million electric vehicles a year. And one of the reasons why EVs are so enabling is this end-use efficiency point. Tesla Model 3, it's 4 times more efficient from the well to wheel than a Toyota Corolla. And that's all about the efficiency of getting the electricity into the car in a sustainable energy economy, and then how efficient the car is in transferring that stored energy to motion on the road. Next, switching to heat pumps in homes, businesses, and industry. You know, right now heat pumps meet 10% of building heating needs. Install rates growing 10% year-on-year. It really needs to accelerate. Heat pumps can serve, you know, heat applications up to 200 C in businesses and industry. And from an investment perspective, as you can see on this page, this is actually the lowest hanging fruit in terms of displacing fossil fuels. You know, they're all over this factory. They're in your house. And all this really is about bringing them to displace all the fossil fuel heating in all of the homes, business, and in the industry that we can. And from an end-use efficiency perspective, there's a three times reduction in the total energy required to heat these buildings. Next, a little bit more detail on electrifying high-temp sort of industrial chemical processes. So over 50% of industrial heat is greater than 400 C. You know, cement, steel, fertilizers, chemicals, plastics, metals refining all need like 1500 C, so we need a solution here. Ultimately, it's purpose-built equipment that enables electrification. You know, carbon graphite is stable up to 2800 C. There's other options in the 1500 C range, like silicon carbide, other materials. And then on the hydrogen side, we also need green hydrogen to decarbonize metals and chemical refining processes. This is things like ammonia, making steel. You know, there's roughly 120 million tons of hydrogen sourced from fossil fuel today to do these things. And hydrogen can also directly replace coal, which is currently used in a ton of steel production, through a process called directly reducing iron. You can replace blast furnaces with a hydrogen-reducing, direct reduced iron furnace. And this is the way to eliminate fossil fuels from these aspects of the economy. And lastly, a small part of the pie, but a necessary part of the pie, is sustainably fueling planes and boats. Shipping accounts for 3% of global CO2. It's ripe for electrification. Even with lithium iron phosphate, long-haul ships can be fully battery-powered. So that's a great opportunity to electrify. Energy density is a little bit harder for planes, but short haul is doable today. With some improvements, we'll get long haul underway. But even in the meantime, we can leverage sustainable aviation fuels produced and stored using excess renewable electricity. There's a lot of work going on in this space.
Yeah, I mean, to really get long-range aircraft and long-range shipping to use lithium-ion, you need to redesign the ship and not just...
or the plane.
And the plane. To take advantage of the fact that it is a new source of energy. It's a different architecture. Make it mass efficient and optimized for batteries. The same, if that's done with aircraft, I think you can get long-range aircraft at around with cells at around 450 watt-hours per kilogram, which you can buy it right now. Actually, they're expensive, but I think that price will come down.
So when we stack up all of these efforts, we end up with the numbers we shared at the beginning of the presentation. 30 terawatts, 240 terawatt hours, $10 trillion. And you may be saying, like, I need some context. Is this feasible? Spoiler alert, it's entirely feasible. Just looking at it from a growth rate perspective, how much do we need to grow the deployment of these technologies? We're talking about only a 3x growth rate in solar and wind deployment. When we look at the electric vehicles, they have to grow 11x. Well, they grew 60% year on year last year. That growth rate is also going to close pretty darn. That gap is going to close pretty quickly as well. And lastly, storage. Tesla's energy storage business has grown at 65% CAGR since 2016. The global energy storage business is accelerating pace as well. I mean, all these gaps are going to close, especially as this momentum of the transition to sustainable energy accelerates. And of course, our goal on this page is 20 million EVs per year and 1 terawatt hour of stationary storage per year, basically as soon as we can. And then, what about this investment? How do I have a reference point on this investment? Elon mentioned it's 10% of 1 year's world GDP. Another way of thinking about it is how does it compare to what we're investing, like what we invested last year in the fossil fuel infrastructure? And it's 60% of that investment. So actually, building this sustainable energy economy is less than extending the fossil fuel economy from a year-over-year investment basis. So very doable.
Yeah.
And what about on the mineral extraction side? So this is a cartoon that sort of gives you a sense for all the ore and the extracted minerals that are coming out of the earth every year. It's about 68 gigatons. So each truck is a gigaton. What does this look like when we're in a sustainable energy economy? Looks like that. The fossil fuel extraction disappears. We replace it with the materials required to fulfill the sustainable energy economy. It actually reduces. And then when we calculate it on a sort of element by element basis, the resources are there to support the transition. This is cumulative demand to move in the sustainable energy economy direction until 2050 relative to USGS resources today. We're not breaking the resource bank for any of these materials. And then when we look at what really happens as we move forward, history teaches the more we look, the more we find. We go through this effort, we build these batteries, and then we recycle these batteries. So ultimately, we're doing this to build this sustainable energy economy, but the maintenance amount of ore that we require is really an order of magnitude or more, less, because of recycling. So in the end, a sustainable energy economy is within our reach, and we should accelerate it.
Yeah, I mean, so this is really the main message of today. And I really wanted today to be not just about Tesla investors who own stock, but really anyone who is an investor in Earth. And what we're trying to convey is a message of hope and optimism. And optimism that is based on actual physics and real calculations. It's not wishful thinking. Earth can and will move to a sustainable energy economy, and will do so in your lifetime. Thank you.
Yes. Thank you. And I just want to welcome up Lars and Franz to the stage.
So when you think about what I'm trying to say, I really want to hammer this home. When you have a car that's about 5 meters long, and you have people working around it like we did in Model 3, and we change that to this process where we take different parts of the car, and we can do more at the same time, like we did with the Model Y structural battery pack. What you see here is us doing that on the front part of the vehicle, or the rear part of the vehicle. That means we can get more people working on the car, or robots, working on it at the same time. That means we have better operator density, less time doing nothing. We get 44% more operator density, which means more work, less time walking back to the station, 30% improvement in space-time efficiency. And because we're not building it in and out of the car with those slow movements of those robots I showed you from production hell, when we go to automate it, it's going to be a lot easier. In the end, that will probably look something like this, where we balance parallel and series manufacturing in a way where we only do things that are necessary, with a much shorter final line, blocking a lot less of the entire rest of the factory, so we can optimize material flow using the best practices. And what that means, it's going to look something like this, where we build all the sides of the cars independently. We only paint what we need to. And then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it. And it means we're doing more work on the car more of the time. And then when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time, just like Cybertruck. So in the end, you get the same car, but it's not going to be a Model Y.
Yeah, this is not. Yeah. This is a Model Y for illustration, not the next-gen vehicle.
In the end, what does that mean? To increase the scale and adoption of electric vehicles on the orders of magnitude that we just showed you, we have to make constraints part of the solution. It leads us to greater than 40% reduction in footprint, which means we can build factories faster, with less CapEx and more output per unit. We'll reduce costs as much as 50%. This is the 2-for-1 concept you hear me and Elon talking about on earnings calls.
Yeah, so I think our track record proves that we can deliver the best cars, and we deliver the best cars in spite of, because of these constraints. And I'd love to really show you what I mean and unveil the next-gen car. But you're going to have to trust me on that until a later date.
Thank you, Franz. My name is Colin Campbell, and I have the real privilege of leading powertrain engineering here at Tesla. And the powertrain factory, which is behind me today, is 75% smaller and 65% cheaper than the one that we originally built. In our next powertrain, so those silicon carbide transistors that I mentioned that are key component but expensive, we figured out a way to use 75% less without compromising the performance or the efficiency of the car. And of course, we know that battery cell supply is one of the constraints on the scalability of EVs right now. Our new powertrain is compatible with any battery chemistry. And that will give us great flexibility in battery sourcing. If we want to make EVs more accessible to people, they have to be cheaper. We've reduced the drive unit cost to about $1,000. And we don't think any other automaker is even close to that number. We have designed our next drive unit, which uses a permanent magnet motor, to not use any rare earth materials at all. And this achievement, like all of the achievements that I mentioned today, it's only possible because of the incredible people on our powertrain teams. They are absolutely committed to the cause of sustainable energy, and that is why we can do what no other company can do.
Good afternoon, everybody, and welcome to Texas. For Cybertruck, we are now designing 85% of the controllers in the car. For the next-gen platform, we're going to finish the job and be designing 100% of the controllers to give us full control of the design and the supply chain at the component level.
Thanks, David and Pete. Hey, everyone. My name is Ashok Kelliswamy. I work on autopilot and self-driving. Like I mentioned earlier, the solution to scalable FSD is getting the AI architecture, the data, and the compute just right. And we have assembled a world-class team to execute on this. We are pushing the frontier on these 3 items, and as we improve the safety, the reliability, and the comfort of our system, we can then unlock driverless operations, which then makes the car be used way more than what it is used right now. With that, I'd like to introduce Elon back on stage to give some more updates.
It's kind of weird seeing the arms and legs just separate. Worth bearing in mind that when we did AI Day, this version of Optimus didn't walk at all. So the rate of improvement here, I think, is quite significant. We have the real-world AI. We're the most advanced in real-world AI. So the same AI that drives the car, which you can think of the car really as a robot on wheels, and this is a robot on legs. So as we solve real-world AI, and I don't think there's anyone even close to Tesla on solving real-world AI. That same computer and software goes into Optimus. Probably the least understood or appreciated part of what we're doing at Tesla, but will probably be worth significantly more than the car side of things long term.
Hi there. My name is Rebecca Tanucci, and I lead our charging infrastructure teams here at Tesla. Recently, we have started opening up our networks on a global basis. Over 50% of our superchargers in Europe are currently open to other electric vehicles. We've also opened up in Asia Pacific with our first sites in Australia. And just yesterday, we opened our first 10 supercharger sites here in North America and the US to other electric vehicles. We've also just started installing our 4th generation supercharger posts. Those are being installed in Europe first. And while it's not a big mention, not a big thing to mention, they do have longer charging cables so that we can more easily reach the charge ports of different vehicles.
Hi, my name is Karn, and my team leads supply chain for electronics, powertrain, and battery at Tesla. So the question gets asked, is Tesla going to basically break the chip industry if we grow to 20 million vehicles? The answer is no.
So in a line that would need 1,000 associates to build the super manifold in full volume now just takes 10 associates.
Hi, everyone. My name is Tom Zhu. I'm now responsible for global production and sales and delivery service. I joined the company back in 2014, and I've been running the company's business in Greater China and APAC. Today, I'm representing all the gigafactories and talk about how we can make more cars and faster. I'm happy to share, early this morning, we hit the 4 million mark for total Tesla ever built. If you look at the chart on the left, Shanghai be able to significantly drop our labor hours per car during the ramp. The little dip there has happened in the last Q2 2022 because of the COVID shutdown. And on the right is the Fremont Model Y shop. Even this is a 6-year-old facility, the team there still be able to optimize the material flow, eliminate all the single point of failure, and drive higher output, hence reduce the labor hours. And actually, this factory keeps setting a new record. Yesterday, they just had a new factory daily record.
And we've also continued to focus on refining the way we make cells and the factories that the cells go inside. As you can see on this chart, from typical 2170 cylindrical cells to 4680, we made a huge leap, which is basically a 5x reduction in the factory footprint and volume and footprint. And then from going from what we did in Fremont and our pilot line to Texas, we improved further, and we're improving again when we go into Nevada. And what this actually represents is a series of actions taken by a very integrated, holistic design team across the product design, the manufacturing design, the process design, the equipment design, and the facility design. And we're not just looking at the cell factory itself, but also upstream materials where necessary. What you see here is the rendering of the 50 gigawatt hour a year Corpus Christi lithium refinery that we've already broken ground on here in Texas. The facility will start commissioning by the end of 2023, this year. This is a good example of something where we're basically talking about breaking ground and starting commissioning within 10 months, and with actual production within 12 months. That's the target, similar to what we did in Shanghai. And with that, I think that sums up our efforts on the factory side. Mike, you want to come up and we'll talk about energy?
All right. We're on our 6th generation of our industrial product, which is the Megapack XL that we're building out of Lathrop, California. We've deployed over 16 gigawatt hours of industrial and residential products across 50 countries. And really, Megapack is a market leader. It's best in class in efficiency, reliability, energy density, and easiest to install, lowest cost to install.
So putting this all together, we're really at the beginning of this massive ramp in energy storage deployment.
All right, so this is our last section of our prepared remarks today. If we look at our longest running scale production product, this is the Model 3. We reached 5,000 cars per week, which was our design capacity in mid-2018. And since then, we've taken 30% of cost out of this product. Cost reduction doesn't just come from one place. There's no silver bullet here. And as we look forward to our next-gen vehicle, our target is to reduce 50% of cost, and we've talked about that a bit earlier today. Going from the Model S and X platform to the 3 and Y platform, we took out 50% of cost, so the task here is to do it again. And this is very important because as we improve affordability, the number of customers who have access to our products dramatically increases. And as we link this back to our master plan, it enables an exponential growth in our volume with linear reductions in the cost of our products. The second point I'll make here is that, and again, cost reductions don't come from any single one place. But more importantly than just the cost of the car up front, this chart here is showing what the total cost of ownership per mile is over the course of 5 years. And we have to think about financing costs, insurance costs, the cost of power. Drew talked a little bit about that with the plants that we're doing in Texas, wear and tear and maintenance on the cars, et cetera. And we're already at a place today in the US where a base Model 3 on a cost per mile basis is less than a Toyota Corolla, which is the highest selling car in the world. The next thing on cost reduction I want to talk about is operating expenses. We spend a lot of time on our earnings calls talking about gross margins and product cost. We don't spend a lot of time talking about OpEx, but I think this is one of the really important parts of our story. So since 2018, we've reduced our non-GAAP OpEx 60% as a percent of revenue and 75% on a per delivered car basis. This is quite staggering. If we look at the SG&A side of this, I think the story here is pretty dramatic. So we're showing here a comparison of SG&A per car delivered compared to the traditional auto industry, which is both an OEM and the dealership network. And our estimates are that we're 60 to 70% lower on a per car basis. And if you turn this into dollars, this is many thousands of dollars per car. So to wrap up the finance portion of the presentation today, couple of key messages I just want to leave you all with here is that we use innovation at an intense level to drive costs down and improve the efficiency of the business. And the reason this is so important is it allows us to improve product affordability. And this is particularly the case when we move to our next generation platform. Improving affordability allows us to comfortably make investments that grow volume. That volume generates cash that then allows us to make more investments. And as we integrate that going forward, it's our belief as a leadership team here at Tesla that we're going to achieve unprecedented scale in the manufacturing space. And this is what's ultimately required to accelerate the world's transition to sustainable energy. Thank you all very much.